İyiyiz hocam, sağ olun siz.
Teşekkürler. Herhangi bir sorusu olan var mı?
Hocam bu dönem daha ödev gelecek mi?
Yok, bu son ödevdi.
Tamam hocam.
O zaman başlayalım arkadaşlar. So today's lecture is going to be about sampling theory. So here's the outline. We're going to cover the convolution property of the Fourier transform, then move to the sampling theorem, and we have interpolation process, which is a reconstruction of a signal from its samples. Of course, it's collected at the Nyquist rate, so we will introduce Nyquist rate. But what happens if we sample at a smaller than Nyquist rate, which is going to create a aliasing problem? How do we handle this aliasing problem? And the last topic is going to be pulse code modulation, PCM. So you guys know the convolution by your heart, I guess. So let's refresh your mind. The time convolution in time domain. Assume that we have two signals, G1 of t and G2 of t. If we convolve these two signals in time domain, and it corresponds to the multiplication of this signal in frequency domain, which is capital G1 of W times G2 of W. So similarly, we have a duality, means that if we convolve these two signals in the frequency domain, it corresponds to the multiplication of this signal in time domain. And if you guys remember, what was the definition of the convolution? Let's say we have a G of t and W of t signal, and convolution of these two in time domain is equal to integration from minus infinity to infinity, G of tau times W, t minus tau d tau. That was the definition of the time convolution. So what's the filtering means in signals and systems literature? And so, you know, system actually can be considered as a filter, and we have different types of filter, and the filter type that we consider, or the system type that we consider, is LTI, linear time invariant system or filter. In this case, if you apply the delta of t impulse signal, at the end you will obtain the impulse response, which is h of t. And the relationship between the input and output of the system, and it's governed by the convolution, if you guys remember. For any input of x of t, the filter output. So a filter is a special case of system. So far we were talking about the system. Now we are talking about some implementation and some use case, which is a filter. And the filter output is equal to convolution of input x of t with the h of t, which is the impulse response of the system. And sampling, because our topic is sampling, we are trying to give you some background in order to explain the sampling theorem. So in time domain, we have x of t, h of t, and the output was convolution of input with the impulse response. And this operation in frequency domain, according to the previous property of convolution, the input is x of f, and our system function is h of f, and the output is going to be multiplication of input with the system function. In our case, it's h of f times x of f. So these concepts will be useful when we talk about some sampling issues and related mechanisms such as interpolation. So, as you see, the convolution involved to this messy integration in order to avoid and to study the filtering in the frequency domain, which is just a simple multiplication. So that's why we prefer to study in frequency domain. Okay, after this mathematical background, now we are ready to talk about the sampling theorem. So let's start with the definition. A technical definition is given as follows. Any signal band limited to B hertz, bandwidth hertz, B hertz, can be reconstructed exactly with error-free from its samples taken uniformly at a rate greater than 2 times of this bandwidth. In other words, minimum sampling frequency is going to be equal to 2 times the bandwidth of your signal. And this rate fs, which is equal to 2 times of bandwidth of your signal, is called Nyquist rate. So these very fundamental things in any kind of electronic and the computer system. So most of the signal in practice are analog, and we need to convert this into the digital by sampling, right? So, but the question is, if you sample a signal, and the question is, at what rate you're going to sample? So if you don't sample with the proper rate, and you transmit the signal on the other side, the receiver side, there's a computer, and the computer is going to receive these samples in digital environment, and you need to reconstruct your signal, your information from these samples. So that's why it's really important at the transmitter side, at the sender side, at which rate you are sampling, because this is going to affect the reconstruction mechanism at the receiver side. So this can be a voice, this can be a video, it can be an image, it can be a data, it can be a text. So whatever, and when you sample this information, this signal, you need to be careful. And at least rule of thumbs, you need to minimum sample at the Nyquist rate, which is 2 times of the bandwidth of your signal. Okay, so that was the verbal explanation. Let's look at more mathematical and visually how this sampling happens. We have the x of course, this sampling in time we are talking about, and we have the sampling in the frequency as well. So this is the sampling that is done in the time domain. Let's say this is my information x of t, which can be a image, video, or voice, or a text or data, is a kind of a cryptocurrency, or stock of a company, or a temperature of a Gebze, and so on. So we need to digitize this in order to transmit or process or modify, whatever you call, this signal. So that's why the first step is to digitize, to collect the samples. So what does it mean mathematically? I'm going to multiply with this impulse train. We call it impulse train. Delta, which is the duration between each of these two impulses, equal to Ts. And Ts, we call it sampling time. So how often you are going to collect the sample from this x of t. And this is determined by the Ts, sampling time. If you decrease this Ts, you're going to collect more samples. If you increase this Ts, parameter sampling time, you are going to collect less number of samples. So what does it mean by collecting? Mathematically, you multiply this x of t with this impulse train, which is separated by ts time, sampling time. And if you multiply visually, it looks like this. This impulse takes the value of this value. This impulse takes this value. This impulse takes the shape of this signal basically, and is collected for every ts sampling time. So that is my sampled signal. So this is basically sampling in time. And what's the corresponding operation in frequency domain? Is, if you guys remember, multiplication in time correspond to the convolution in frequency domain. So that's why the Fourier transform of x of t is equal to x of f. And it has a bandwidth of b, as you see. So this is my bandwidth b signal. And the delta impulse train, if you apply the Fourier transform, it's a impulse train that are separated by 1 over Ts, also known as Fs, which is the sampling frequency. In this case, we just multiply this shape with this impulse train and we obtain this one. But in this case, not a multiplication, is a convolution. That's why we're going to pass over this triangle shape over this impulse train. And if you apply the convolution, it's going to look like this. You pass over all these and you see blue one, red one, and green one. And the center of each of this information or triangle is separated by 1 over Ts, which is my Fs. 1 over Ts is equal to Fs, my sampling frequency. Now remember, Nyquist rate was equal to 2 times bandwidth and must be greater or equal. So in this case, we have a B from here and B from here. So Fs in this case is equal to exactly 2B. If it was a less than 2B, what would happen? What would happen? In this triangle, they will start to overlap. They will start to mix each other. And this is, at the sender side. And it's really hard to extract or separate these copies at the receiver side. Under what condition? If the Fs was less than 2 times of bandwidth B. So that's why Nyquist rate says the Fs, which is equal to 1 over Ts, must be greater than 2 times of bandwidth so that you can separate these copies, because these are the same information that you are replicating, copying every Fs. So that's why we need to follow Nyquist rate at the transmitter side so that we can separate mostly the copy in the center at t equal to 0. So F equal to 0, I'm sorry, so that we can extract this information without overlapping with other neighbor adjacent copies when we reconstruct this information at the receiver side. So this is the sampling in time domain. If you collect the samples every Ts, this is what happens in the frequency domain. Okay, so We have some notation. So X correspond to the time domain, S correspond to the frequency domain. So let's remember the Fourier transform pair. And this is my f of x in time domain, means f of t. If I apply the Fourier transform, assume that it has this signal in the frequency domain, which is f of s. So the key idea here, what we are trying to show, a time domain signal is fully characterized by its Fourier transform. So you can apply the inverse Fourier transform to get back this information to the time domain. So you transfer this information from time domain to the frequency, and you can apply the inverse Fourier transform to get back this information from frequency to the time domain. So it's not lost, basically. So once you transfer into the frequency domain, don't think that you cannot get back this information to the time domain. So with the inverse Fourier transform, yes, you can convert back to the time domain. So let's remember the Fourier transform of cosine. This is a cosine signal in time domain, which is a periodic, as you see. And if you apply the Fourier transform, and you'll see that it consists of two impulse response. One of them is centered at W, the other is centered at minus W, and they are symmetric, as you see. So Fourier transform of a pulse train, remember from here, this is the pulse train, also is a pulse train in the frequency domain. So that is, let's say the separation between pulses is W. When you apply the Fourier transform, the separation between two pulses is going to be minus 2 pi over W. So that's the relationship between pulse train in frequency domain as well as in the time domain. So why we are studying this is to introduce some of the practical problem that we came across when we apply the sampling. So this is my f of x in time domain. This is my information, which can be voice, video, image, text, whatever. So if I sample with the sample frequency of W in the time. So as you see, in frequency W, we have the pulse train, and you pass this shape over this each of these pulse train, and at the end of the convolution, so the effect, the output is going to be replication of this information every W, every pulse train. So you make a copy of the same signal every W in this case. But, you know, if you don't follow the Nyquist rate in this case, as you see the side lobe of this signal, copy of the signal, they start to overlap each other. They start to mix each other, as you see. So originally it was like this one because of the, we don't follow the Nyquist rate, and the side lobe of each copy start to overlap each other. And that is going to create a problem because this side lobe also contains some of the information about your voice, about the video or image that you are transmitting. So we need to take care of this problem. And in time domain, remember guys, we have this signal, which is a, voice, video, image, or text, or data, or a temperature of Gebze for a week. And we need to sample this. And in order to sample this signal, we multiply with the pulse train in time domain. And you multiply the signal with the pulse train, the output, the sample signal is going to take the shape of these pulses, right? So the output is going to looks like this shape, but consists of value at only this pulse. So it takes this discrete value, this discrete value, this discrete value, this discrete value. So I convert, or I sample, a continuous time into a discrete time signal. Previously, it has a value for every t. Now it has value only every ts, which is my sampling time. So I collected some certain amount of samples. In this case, 1, 2, 3, 4, 5, 6, 7, 8. So I collect only 8 values from this continuous time signal. If I follow the Nyquist rate, I may be able to reconstruct this original shape, original information at the receiver side. Okay, so let's look at the Nyquist rate, which is very important in sampling theory. And that was my original signal that contains of information. And if I apply this Fourier transform, let's assume it has this signal, the Fourier transform of this signal, assume that it has this signal in frequency domain. And I just did previously, if I sample this continuous time by multiplication with the pulse train that are separated by TS sampling time, and the output is going to have this discrete time signal consist of 8 values that has a shape of this original signal. That's what's happening in time. But in the frequency, as we said, multiplication with the pulse means convolution of this signal, this shape, with the pulse range. So you replicate, you copy this signal every TS. In this case, is 2 pi over W. Because if I follow the sampling time, Nyquist rate in this case, as you see, the side lobes, they didn't overlap each other. So they didn't overlap each other. So that's why I can reconstruct easily at the receiver side. And let's look at the signal reconstruction at the receiver side. That is the transmitter side. I sample it and send this sample through the Wi-Fi or 3G or mobile networks. And I receive these samples. So my job is to reconstruct this information from this sample. How am I gonna do that? It's called interpolation. So in other words, use a rectangular filter to get rid of the redundant replicas of the spectrum. So what I'm gonna do is basically in frequency domain, I just use a rectangular filter that has a shape of rectangular to extract the copy at the center and then remove the other copies, cancel out the other copies. In frequency, this is called filtering. So, and what does it mean in time domain? Since this is a rectangular, we just multiply the rectangular shape with this signal, right? And what's happening in time domain? If you apply this, if you apply the Fourier transform to the rectangular shape, you obtain this in the time domain. So the inverse Fourier of this rectangular shape signal is equal to this in time domain. And we multiply this rectangular with this frequency. Multiplication correspond to the convolution in time domain. So I just multiply this to extract and cancel the other copies in frequency domain. In time domain, I'm passing this continuous time signal over these discrete values. So as I pass over this, as if I am, connecting these dots basically. So I'm filling out the gaps between these two discrete values. And this is gonna be result looks like because of the filtering. This is how we reconstruct the original signal. Original signal was this. And at the receiver side, I reconstructed from these samples by convolution of this with this signal. So visually, it means you are filling out these gaps between two values. And you are connecting the dots so that you can come up with this original signal, original shape. And this process is called interpolation. Simply is a signal reconstruction from the samples. So let's look at the time domain interpretation for the interpolation. And because multiplication in frequency domain, we said is the convolution in time domain. So we convolve the sinc function with the samples that we have. That was the filter that we multiply with the multiple copies to extract the central copy and get rid of the other adjacent copies. So that's how we reconstruct. But this corresponds to the convolution of this sinc function, which has a side lobes with the samples as if you are passing through this pulse train to fill out the gaps between two discrete values. But, we have some problems if the signal is undersampled. What's the undersampling means? If your sampling time is smaller than the Nyquist rate. In other words, the FS sampling frequency is less than 2 times of the bandwidth of your signal, then we are in trouble. Because as you remember, guys, that was my signal in the frequency domain. When I sample it, I convolve with this pulse train, make a copy for every T pi over W for FS. And when I make a copy or replicate every FS, as you see, these side lobes, they start to overlap to each other. They start to mix each other. So when they mix each other, they add them up or cancel out, and I lost this information. And the reconstruction of such signal back becomes not possible. So what's the solution to solve this problem? It's called anti-aliasing filter. So the simple idea behind the anti-aliasing filter is this problem is called aliasing because of the side lobes of the copies start to overlap each other and you lost this part. And this problem is called aliasing. What's the solution for aliasing problem? Is to utilize anti-aliasing filter. And the main idea behind is to sacrifice the overlapping segments. Let's see how this anti-aliasing filter solve the problem. So before we sample any signal, we pass through a sharp, it looks like this red sharp rectangular filter to get rid of this problematic part, which are the parts that they are going to overlap to the other copies in both sides. So we get rid of this, the tail spectrum that will lead to the aliasing problem. So from the beginning, before the sampling, we cut and get rid of these tails to avoid the aliasing problem. Of course, when you cut this, this part consists of some information about your signal, which is part of your image or video or text, whatever, but still is tolerable. So you lose some information, of course, but it's better than facing the aliasing problem, which yields more problems. So that's why before we sample this, and it's gonna looks like this, as you see, and then after we sample means we make a replication. We copy for every FS, as you see. Now the tails not overlapping, so that means there is no aliasing. With this simple but practical solution, we solve the aliasing problem. And that was in the frequency domain interpretation. Let's look at the aliasing in the time domain. So this is my time domain signal, and then I multiply with the pulse train, and I end up with these discrete time values, 1, 2, 3, 4. So I represent this continuous time signal with 4 values, 4 discrete time values. So, and because we didn't follow the Nyquist rate, we sampled every TS, in other words, is equal to 1 over Fs. So we represent this signal with 4 values. And when we reconstruct this at the receiver side, this is gonna be looks like this. As you see, this is the reconstructed signal, and this is the original signal. Of course, it looks kind of similar, but there's a difference, and because of the aliasing problem. So we didn't follow the Nyquist rate. For instance, if I follow Nyquist rate in this example, I may need at least maybe 8 samples so that I can reconstruct this original signal. But because of I reduced the number of samples to represent this signal, now I lost some information, and the reconstructed signal is this, and it's way different than the original signal. So this is the effect of the aliasing in time domain. For sampling, now let's talk about the use case, how we transmit these samples, sampled signal, and what are the practical problems. Any questions so far? Okay, let's have a 10 minutes break then.